Quantum uncertainty says that you never simultaneously know the exact position and the exact speed of an object. But the question is, why can't we do this in quantum physics, whereas it is possible to do it in classical physics? In this video, we will know why the position and momentum of the object cannot be measured simultaneously in quantum physics. According to the quantum uncertainty principle, if we try to measure the position and momentum of any object simultaneously, there is uncertainty in the measurement of both. Never the position and momentum of the object can be simultaneously measured with 100% certainty. The multiple of this uncertainty in position and momentum will always be equal or greater than h upon 4 pi. If the uncertainty in position is reduced, then the uncertainty in momentum will increase and vice versa. But never it will be less than h upon 4 pi. It is also represented by h bar by 2, where h bar is modified Planck constant. Here the symbol delta used for uncertainty is not a standard notation. We'll write this relation later in standard form. The uncertainty principle exists because according to de Broglie principle, everything in nature behaves like a particle and wave at the same time, which is called wave-particle duality. To understand this, first let's understand what is meant by wave and particle-like behavior of an object. Particle means to be on one single position at an instant time, which can be easily defined that where is the particle in space and where is not. The same, wave is a disturbance spread in the space. There are some features which identify the property of wave. One of them is wavelength. Wavelength is the distance between two peaks or two valleys, but there is no single position in the wave like particle. Each peak of the wave indicates the probability that particle is present here. It has finite probability of being in many places. Wavelength is very important in quantum physics because according to de Broglie, the wavelength of an object is associated with its momentum. According to de Broglie, the corresponding wavelength of an object is inversely proportional to the momentum of that object. The greater the momentum is, the shorter the wavelength. Momentum, which is mass into velocity, a fast-moving body or a heavy object has a lot of momentum, which means the wavelength associated with such a body will be quite short. The wavelength associated with our everyday object is quite short, such as tennis ball. The wavelength of a tennis ball is so low that it cannot even be detected. While small things such as the electron, the wavelength associated with electrons are almost the order of nanometer, almost equal to the wavelength of visible light, such a large that can be measured in physics experiments. So, if we talk about the pure wavelength of a wave, it will have fixed momentum, but there will be no fixed position because the wave will be spread in whole space. That means particle can be anywhere in the entire space. On the other hand, you can specify the position of the particle, but nothing of its momentum will be known. But why? In classical physics, the particle's momentum can be described with position. Then why not in quantum physics? This is because in classical physics, both position and momentum have properties of particles, which are defined in the same picture. In classical physics, the position tells where the particle is, and the momentum is multiple of the mass and velocity of that particle. But in quantum physics, position is the property of particle, but momentum is the property of wave. In quantum physics, the position tells where the particle is, but the momentum is not multiple of its mass and velocity. Rather, it is inversely proportional to the wavelength of the wave associated with the object. To bring both the position and momentum of an object together, we have to mix these two different pictures. For this, we need a wave which is confined in a small area, so that the uncertainty in position becomes certain for a fixed reason, not for the entire space. But how will this happen? If we have a wave, it will have a definite momentum. But if the two waves of different wavelength combine, then the momentum can be either of the two, which means the momentum will become uncertain. But one advantage of this is, due to the interference of the wave, where two peaks or two valleys will be matched, there will be a wave of higher amplitude. And where a peak and a valley are matched, both will cancel each other. By doing this, we will get a wave in which the wave will be separated by such regions of nothing. If more waves are combined, the final wave will become confined in a small region and the nothing portion become larger. So finally we have a wave that is confined in a small region, which means the uncertainty in position is less. But when this happened, because of so many waves, the uncertainty in the momentum increased. We can make the position more certain, but then momentum will become equally uncertain. This is the quantum object, which has both particle and wave-like behavior. And because of this behavior, there is always uncertainty in them. If we reduce the uncertainty in one, it will increase in the other, and multiple of their uncertainty will never be less than h upon 4 pi. This principle was first introduced by Heisenberg. But two questions still remain. First is that, how will we calculate uncertainty? What does this physical mean? Actually, uncertainty is the standard deviation in the measurement of quantity. This is the actual relation of uncertainty in position and momentum, where sigma represents a standard deviation in measurement of position and momentum. Second question is, why is this relation found with few physical terms? Means the uncertainty of the position is only with momentum. But why not with anyone else? Well, the answer of both these questions we will get into the next part of quantum uncertainty.